All right, so now the recording started. Today we'll wrap up the last topic I want to cover before the midterm, and to be honest, to finish up the CPU side of things, right? So we have talked about multiple techniques to get more performance out of your CPU, and how most company would basically design kind of like the preliminary version of their CPU, right? The next thing I want to cover is basically, now that we talk about the design on the CPU side of things, right? We forgot and we kind of discard one big elephant in the room, which is the load and store instruction. Anything that has to do with memory, right? Because what we consider so far is when we fetch, you have to go to the memory and it takes one cycle. Somehow the memory is magical, right? You go there and say, hey, I want this data. The memory comes back with your data in one cycle. Accessing a data is also free in the sense that it takes only one cycle, but both are not true. In reality, this takes a lot longer. And in the second half of the class, we will talk about many of the um, classic method to tackle this problem, and so that most of the memory operation is really ended up being pretty fast. Right, and I stress on the word most, but today I will talk about what would happen if you run into a load and store instruction and how to handle that in the more like instruction window style, so we can still have a imitating data flow machine, right? Generally, DRAM takes a lot longer to access, right? And also the memory is also limited, right? So there's so many things going on right now in the system to make sure that you have the illusion that whenever you want to access your data is fast and it's free, right? Now we'll start to crack that illusion and see how this magic happened one step at a time. Today we'll just cover what happened on the CPU side of things when you have memory instruction, right? So when you have out of order instruction, sometimes you run into memory instruction like, I want to read the content of this address. I want to write something to this address, right? You want to make sure the first thing first, with out of order execution, right? At the end of the day, it had to still follow the same pattern. If you want to write something or read something to your DRAM, that has to be done in order. It has to be done one at a time, one by one by one by one. So you have this dependency between the previous load instruction and the future load instruction that comes in that's already in your scheduling window, right? So the scheduling window is where you fetch a bunch of instruction and you try to figure out, okay, who can go and get issue the new operation, right? Now, the key here is first, how do we detect the dependency? Should we just wait until all the store are committed, or should we kind of figuring out like, okay, if I want to write some content to this address, let's say you have address 20, right? You store to address 20. And then you have the load instruction to address 20 afterward. What can you know? So let's say you're still waiting for DRAM to write some number to address 20, and then after 5 load instruction come in and say, hey, I want to load what's in address 20. What can you tell here? What can you tell here? So let me first ask this first question. Who is trying to update address 20 right now? The store or the load, or there's no updates happening? All right, so let me repeat the question again. Both of these are in the pipeline. The earlier instructions say, hey, I want to update the content at address 20 to, let's say, 5. And then in the future, 5 more instruction, you see the load instruction that say, hey, I want to load whatever's in address 20. What can you tell about the data being loaded? What's the value? So what would be the value of the data being loaded? Do we have to go to DRAM, or is the value available somewhere? Yeah, the previous store, while it's still finishing up the store, you have the value, right? In the CPU, right in the CPU, the store instruction has the value. So what you can do is say, hey, the new load instruction that come in, say, hey, I want address 20. Check the store. The CPU basically, instead of going to the main memory, what you can do is to check the store buffer. We'll talk about the store buffer next, like how it's structured. But basically, you can check like, hey, there's a previous store to that address, so get that value. You don't have to go to DRAM because that takes a long time, right? So this is how you can treat the load instruction. But the question again is, you can have a bunch of things happening at the same time, and sometimes you don't know that you want to load address 20. Sometimes you don't even know the address you're loading until later on, right? So today we kind of cover what to do. The first thing we can tell for sure, right? You can forward the store data to the future load instruction, and modern processor does this, right? It uses a structure called a load and store queue, to do exactly that. I'll show you how, right? But the first obvious part, right? The obvious part, when you have a load instruction coming in, basically you just fetch a load instruction. One thing you can do is to go look at the store queue. And once you know the address, just check the store queue and see, anyone try to store to that address, so that I can take the data and don't have to go to DRAM, right? So that's the obvious part. The second not so obvious part is when you have a store instruction, right? I have out of order execution. So my store, which supposed to happen before the load, right? Before the load, it gets scheduled afterward because I don't know the address. Once I know the address, some future load already is in the scaling window, right? So one thing you can do is if you have a store instruction that comes in, I can check, hey, who needs that data? So I can forward it right away as well, right? And you can also have a combined load store queue as well to make sure you save a little bit of space. But in the end, right, what you have in your CPU is something called the load store unit. This is used to handle. This can be used to handle load store when you have out of order scheduling, right? One quick thing that I want to make sure I point this out. My write to DRAM never block the pipeline because it just produces the data to the address. As long as the store buffer has the data, future loads can always check the store buffer. A future load always can check the store buffer and get the data. So store or write to DRAM doesn't slow down the CPU. It doesn't slow down the CPU. What slow down your CPU is when you want to read the data, because that blocks the pipeline, right? And the question here that I'm going to show you in an example in the next slide is, what if you're loading something that you stored earlier? So here's the structure of the load store unit, right? What do we actually need? Let's assume we have out of order scheduling, right? The buffer would have the type of the load and store. Is it reading or writing to the memory, right? What's the address you're trying to load and store into? And what would be your data? If you have your data ready, it means that whoever wants that value takes the data away, because that's the correct version of the data, so that you can have out of order execution going in. Right, so it is allow pipeline to run in an out of order fashion. load and store can be done independently of future instruction. So let's say I have future instruction coming in. It doesn't have any dependency to the load instruction. I can schedule that, right? And if you have future instruction that needs the data from this address, I can also forward the data to the load. So here's an example. Let's say you have a load buffer and a store buffer, right? Now, in the load buffer, the first load I saw is like, I want to load to address A. So any variable here is an address. So I want to load to A. Then I have a load to B. I have a load to B. Well, what happened right now is I issued two loads to DRAM at address A and B. So these are obvious, right? Now let's say I have load A again. I have load A again. Let me ask you the first question. Do I really have to go and load the same address again, or do I just kind of like merge the two together? We can merge, right? So one thing for sure is you can have a structure to make sure you don't send two separate requests to address A, because that's going to be the exact same data, right? So that's one thing. So we're going to cover that through a structure called MSHR that's covered in caching. For now, you can right now just make sure you understand that if you have two loads to the same address at around the same time, if they are the same copy of the data, the CPU will try to minimize the amount of memory requests basically to this address, right? Because they are actually loading the same data, right? So that's our first observation. So let's say time continues on. You're trying to service the load, right? Now a store coming. I have a store to A with a new data. So that's why I use a different color. So the color red and the color blue, even though it's to the same address, they are different versions. There's a blue version and the red version of the data, right? Then let's say I have store to B. I have a store to B. So B also is the new version of the data. So you're not really using, right? The old data you're loading, which is the yellow version. So now let's say I have a load to A. What can I tell here? Where is the most updated version of my data? Is that in DRAM or is that in the store buffer? It's in a store buffer, right? So you don't even have to go to DRAM. So these long latency access, instead of going to DRAM and spend 50 or 100 cycles, you can then say, hey, I'm going to forward the data right away. This is another form of data forwarding. I have the store address. I forward the data to the future load, right? Because I know what the data is. So I'm basically what I would do is to forward the red data into load A, and I'm done. Let's say I have load B here. Where can I find this data? It's basically coming from the store buffer as well, right? So you can load the new data B to address B right away. So another observation is this. Now you have 5 loads, right? 5 loads. The 2 loads in the beginning have to go to DRAM. The 2 loads at the end finish, right? You don't have to go to DRAM with that. Now let's say I have out of order scheduling. Let's say I have out of order scheduling, and by some magic, right? By some magic. After I have the 2 loads, A here, right before this, you have a store to A, but with the blue version. So what I'm telling you is, what if I have the 2 loads to address A that wants the blue version of the data come before the store to A, but it stored the blue version. It might happen because I don't know what's the store to, like what's the address of my store until afterward, and I already issued the two loads, right? The load to A. Now, in this case, my store would check the load buffer and say, who need that version of A? And it would forward the data, the blue version of the data to load A as well. So then you can just proceed forward and don't have to wait for the data you just issued to DRAM. All right, so that's the less obvious part I said earlier. So let me translate this in Thai just in case, right? Because this is not as obvious. ก็คือเคสเนี้ยครับสมมุติว่าผมมีโหลดที่ address A แต่เป็นเวอร์ชันสีน้ำเงินอะโหลด address A แต่เป็น data ที่เป็นเวอร์ชันสีน้ำเงิน คือจริงๆ sequence ของโปรแกรมเราจะเป็น store A โหลด A โหลด A store A สีน้ำเงินโหลด A สีน้ำเงินแล้วก็โหลด A สีน้ำเงินแต่เพราะว่ามันเป็น out of order scheduling อ่ะสมมุติว่าโหลด A สีน้ำเงินเนี่ยเรารู้ address แต่แรกอยู่แล้วแต่ไอ้ store A สีน้ำเงินเนี่ยเราไม่รู้ address เราก็รอไปก่อนเพราะเราไม่รู้จะ store ไปที่ address อะไรเนาะไอ้เวอร์ชันสีน้ำเงินเนี่ยแล้วพอมัน resolve เสร็จบอกเฮ้ย address ของ A มันเป็น address ของ store เนี่ยคือ address A เพราะฉะนั้นมันก็เลยรู้แล้วว่าเฮ้ยมันเป็น store สำหรับไอ้โหลด2ตัวนี้ไอ้โหลดสีน้ำเงิน2ตัวเนี้ยเพราะฉะนั้นพอผมยัด store ตัวใหม่เข้าไปใน buffer ไอ้ตัวเนี้ยไอ้ store to address A เนี่ยเราก็ไปที่โหลด buffer แล้วก็ไปดูว่าเฮ้ยมีใครต้องการในเวอร์ชันสีน้ำเงินบ้างแล้วก็ไปแจกให้โหลดทั้งหมดไอ้โหลดทั้งหมดที่แบบกำลังนั่งรอ data ของ address A จากแรมอ่ะที่เป็นเวอร์ชันสีน้ำเงินอ่ะมันก็เฮ้ยไม่ต้องรอแล้วนี่หว่าเพราะมี store มาให้แล้วแหละแล้วก็จบนะครับมันก็จะเร็วขึ้นได้อีกโอเคนะครับอันนี้มีใครมีคำถามไหมครับ any questions
แล้วหลังจากที่เรา store A สีแดงไปค่ะมันจะไปทับกันไหม
มันจะทับกันไหมก็คือจริงๆแล้วเนี่ยเราจะ allocate ไอ้สีน้ำเงินก่อนมันจะไปอยู่ใน scheduler ไป scheduling window อะครับเพราะว่า scheduling window เนี่ยมันจะเป็นตัวไว้ดูว่า schedule อะไรได้บ้างแล้ว instruction window มันจะ maintain ไอ้ order นี้ให้เพราะฉะนั้นใน instruction window มันจะเป็น store A สีน้ำเงินตามด้วย store A สีแดงแล้วตามด้วย store B สีเขียวแล้วเราก็จะไม่ retry อยู่ดีเพราะฉะนั้นตัว order เนี่ยมันจะยังถูกต้องอยู่แล้วในความเป็นจริงเพราะว่าผมทำตัวอย่างไม่ค่อยดีไงคือจริงๆมันควรจะแบบ store A สีน้ำเงินมาล่างสุดแต่ว่าไอ้ store A สีน้ำเงินเนี่ยมันจะเป็น store ไปที่อะไรก็ไม่รู้เพราะเราไม่รู้ว่า address มันคืออะไรแล้วก็ store A สีแดงจะพุ่งเข้ามาก่อนแล้วก็ store B สีเขียวพุ่งเข้ามาก่อนแล้วพอเรา resolve address ไอ้สีน้ำเงินนั้นอะว่ามันเฮ้ย address A นะเราก็ไปเช็ค
โอเคค่ะขอบคุณค่ะ
โอเคครับมีคำถามเพิ่มไหมครับเนี่ยเกือบจบแล้ว so stop buffer จริงๆมันหลักการมันคืออันนี้เสร็จแล้ว implementation เนี่ยมันจะเป็นเรื่องของการที่จะเล่นกับว่าเรารู้ address หรือเปล่าเพราะว่าที่เหลือมันตรงไปตรงมามากเลยก็คือถ้าเรารู้ว่า address คืออันเนี้ยแล้วก็ forward นะครับ Alright, so now let's come back to our example right now that there's no more questions. We will ask question afterward as well. So what do we assume here? There's one big thing we assume, which is you always know the address, which is not true. Sometimes you have load and store where you are computing where are you loading to or where you're storing to because you don't know the address until some future steps in the pipeline, right? Memory address can be in the case like you don't know the memory address until you finish the execute steps. Like I want to address R0 plus 4, or I want to address R1 plus 10, right? So it has to wait until you finish doing that add. So the result of this is it's going to be difficult to do the register renaming, right? Because now you have an address that's unknown. You don't even know what's the source, right? And the dependency check is done after the partial execution. Basically, you have to wait until the executes to know the address. And once you know the address, that's when you can do the dependency check. You also have to check the other load and store addresses as well. So that's quite a little bit more involved, right? Because you don't know the address of your operation. Earlier on, you know the register number, like when you do add R1 to R2 and R2 into R3. In that case, you know that you're gonna be taking R1 and R2 together, add them, and then write the result back into R3. So the destination and the source is clear. Now your address is not as clear anymore because you have to wait until the execute step, right? So here's one other issue. Let's say you have a younger load, right? A younger load that have the address ready, because I know the address right away. Let's say you want to load address 10 into R0. Now you know the address is 10. So this is a memory disambiguation problem, which is how can I tell that the previous store is to address 10 because it's still unknown, right? So in this case, there are various techniques across different papers that has been published, as well as different tricks that the CPU manufacturer try to do, right? And there's no correct solution per se. Like there's no de facto the best solution because everything is now based on observation and everything is based on basically science, right? And statistics. But there are multiple ways to handle this. The most conservative, right? So the word I would use is conservative is I'm gonna wait for the address of any previous instruction resolved. So I know all the address before I can issue the load. So I'm gonna stall the load until I exactly know all the addresses. So that's the conservative option. The more aggressive option would be I would assume every single load is independent. So if I know the address of the load, just go to DRAM right away. And then in the future, if there's a store that has the address known, I'll just forward. So that's the same example I showed earlier. So that's the aggressive solution. The intelligent solution is more like I would predict whether the load is dependent on earlier store or not. Right? Because again, the key issue here is if I know my load is independent, I would just issue the request to DRAM because there's no store, there's no previous instruction that's storing to this address, right? So I know for sure it's not in the store buffer. If I know that the load is dependent on previous store, it means that for sure is some of this store instruction in my store buffer, right? So again, let me translate this in Thai just in case it's a little bit confusing here because it's a lot of design decision, right? ก็คือว่ามันเป็น implementation ที่เราเลือกได้ครับเพราะว่าสมมุติเรามีโหลดในอนาคตที่เรา issue อยู่เนี่ยตอนเนี้ยแล้วเราจะต้อง assume ว่าไอ้โหลดตัวเนี้ยมันมี store instruction ไปที่ address เดียวกันหรือเปล่าเนี่ยเราทำได้หลายวิธี conservative หน่อยก็คือว่าเราจะรอจน store instruction ที่เกิดขึ้นก่อนหน้ามันรู้หมดแล้วว่า address ที่มันไปคืออะไรอันนี้เราจะรู้เลยว่าไอ้โหลดตัวเนี้ยมันกำลังจะโหลดไปที่ address ที่เรารู้ก่อนหน้าหรือเปล่าอันนี้คือ conservative option ไอ้ที่เป็น aggressive option คือเราจะ assume ไปเลยว่าโหลดทุกตัวไปที่ address อันใหม่ก็คือโหลดไปที่ address ที่ไม่ได้อยู่ใน store buffer แล้วถ้ามันมี store buffer ตัวไหนที่แบบมี address ที่เรารู้แล้วแบบเฮ้ยรู้แล้วว่า address อันเนี้ยเป็น address A เราค่อยกลับไปที่ดูที่โหลด buffer แล้วก็ไปดูว่าเฮ้ยมีใครโหลดไปที่ A หรือเปล่าเราค่อยแจกให้มันอันนี้ก็ทำได้เหมือนกันแต่ข้อเสียของ aggressive option ก็คือเราจะเปลือง bandwidth กว่าเพราะว่าโหลดมันถูกยิงมาแล้วไงคือเรายิงโหลดแล้วเราไปบอกให้หยุดไม่ได้มันก็จะวิ่งไปที่ DRAM แล้วก็แบบไปโหลดมันก็จะเปลือง bandwidth ที่ DRAM กว่านิดนึงแต่ว่าพอเรารู้ address แล้วไอ้ store buffer มันก็จะให้ data ไปที่โหลดเหมือนกันอย่างที่3ก็คือฉลาดหน่อยก็คือ predict ว่าโหลดตัวเนี้ยมันจะมี store ก่อนหน้าหรือเปล่าไปที่ address เดียวกันอันนี้ก็อาจจะใช้แบบ history predictor ก็ได้ว่าถ้าโหลดที่โปรแกรม counter อันเนี้ยคือ instruction เดิมอันเนี้ยครั้งที่แล้วมัน dependent ก็คือมี store ก่อนหน้าเราก็จะรอจนเรารู้แล้วเพื่อจะไปเอา address นั้นเราจะไม่ต้องยิง request ไปที่ DRAM หรือถ้าเป็น address นี้มันแบบ independent แน่นอนค่อยยิงนะครับมีคำถามไหมครับอีกรอบนึงนะครับเพื่อความชัวร์ก็คือมันเป็นการที่จะต้องการดูว่าไอ้ address ที่เราจะโหลดเนี่ยมัน dependent กับ store ที่มีก่อนหน้าหรือเปล่าเพราะถ้ามีแปลว่าอะไรถ้ามีก็แปลว่าเฮ้ยไอ้ address เนี่ยมีคนจะใช้อ่ะ แต่เรามีคนจะ generate ค่าให้เราด้วยอยู่ใน store instruction แต่ว่าเรายังไม่ได้สามารถ schedule มันได้เพราะเราไม่รู้ address ถ้ามัน dependent นะถ้ามัน dependent เราก็จะไม่ต้องยิง request ไปที่ DRAM แต่ถ้ามันเราจะ assume ว่าทุกอย่างมัน independent หมดก็ได้นะครับก็เป็น aggressive version โอเคมีคำถามไหมครับ Alright so the key problem here with memory disambiguation is, first of all, detection, right? Option 1 again is the conservative option. I'm gonna wait until previous store is committed, so I know exactly, right? I know exactly what is the address. So that's my first option. The second option is I'm gonna keep the list of pending store, the store that are still waiting in the store buffer, so that if you have the address matches, right? Matches to the store address, then I will handle that, right? So that's the two options. And then the second question you have to do is the scheduling. Scheduling is when you issue the load, right? When you want to issue the load. When you want to issue the load, you have load coming in. The first option is I'm going to assume that every single load is dependent, right? So you don't have to do any recovery, but it's going to be slower. The second option is assume every single load is independent, but you might have to re-execute or require some recovery. Basically, if you assume load are independent and you issue that load to DRAM, and let's say it's incorrect, it's depending on some previous store, and it just happened that that load gets serviced first, then you're screwed, right? You're screwed. So you have to make sure you correct the data. Option 3, you predict the dependency of status before you issue that, right? So again, let me translate this in Thai because this is a little bit more challenging, right? ก็คือถ้าเรามีโหลด instruction อยู่แล้วเรา assume ว่ามันเป็น independent โหลดแล้วเรายิงไปที่ RAM แล้วอะไอ้ที่ DRAM อะมันก็ได้รับโหลด request บอกว่าเฮ้ยเราจะโหลด address 20เราจะโหลด address 20แล้วเรา assume ว่า address 20เนี่ยไม่มีใครเคยแก้ก่อนหน้ามัน independent เนาะเพราะฉะนั้นในกรณีนี้เนี่ยถ้าเรา predict ผิดก็คือสมมุติว่ามัน dependent มีใครกำลังจะ store address 20ก่อนหน้าแบบค่า20มันควรจะเป็นเลข5แต่ตอนนี้ใน RAM มันเป็นเลข10อยู่อะแล้วไอ้ store instruction นั้นมันดันช้ากว่าโหลดเราก็โหลดค่าเก่าไปแล้วค่าเก่าที่มันผิดค่าใหม่คือ5ค่าเก่าคือ10แล้วก็โหลดค่า10ไปใช้แล้วอันเนี้ยกรณีเนี้ยก็คือถ้าเรา assume ว่าทุกอย่างมัน independent เนาะเราจะ aggressive อะเราก็ต้อง re-execute คือถ้าบอกรู้ว่าเฮ้ยผิดต้องเนี่ยค่าจริงๆของมันคือ5เพราะมีใครที่จะกำลังอัปเดตอยู่แล้วเราก็ต้อง forward ค่า5นี้ไปให้โหลด instruction ตัวเนี้ยเราก็ execute instruction นั้นใหม่นะครับso that's how recovery and re-execution can be handled, right? The option 3 is a little bit more intelligent, which is predict the dependency status of the load, right? These are the design choices. You can design your own policy, right? And this can impact performance depending on how often you have to recover from incorrect load, right? So that's it for the content of today. So that's it for the new material. The rest are going to be review session to prepare you for the midterm. So first of all, let me stop the recording for this session.